What's up, my stat stars? In this video, we're going to talk about exactly what the 10% condition is and why the heck it is so important. Now, the 10% condition matters a ton when you are sampling. Whether you're looking at sampling distributions, calculating probabilities, using the binomial distribution, finding confidence intervals, or running hypothesis tests, you have to check the 10% condition. And it's really important, but a lot of students don't even understand what the heck they're checking it for. So let's dive into it right now. All right, the 10% condition tells us when you take a sample from a population without replacement, the sample size n should be no more than 10% of the population size, capital N, meaning that your sample size, lowercase n, should be less than or equal than 10% of your population. Now, why is this condition so important? Well, when you sample with replacement, which means every time you take something out of a population, you put it back, well, you always have independence because every time you reach in, the population is exactly as it should be, nothing has changed. But when you sample without replacement, every time you take something out and you don't replace it, and then you take something else out, well, technically that population is changing. So that means every single selection is, well, not independent of the one that came before. And that's a problem, unless we have the 10% condition. The 10% condition ensures that the sample behaves as if it were drawn from an independent process. When sampling without replacement, observations are technically dependent. Each draw slightly changes the composition of the population. But if the sample is small relative to the population, less than 10%, then dependence is negligible and we can assume independence. Now, all that might be fine and dandy, but that still might not make any sense to you whatsoever. Now, at the end of the day, you just have to check the 10% condition, make sure your sample is less than 10% of your population so we can assume independence. Yay! But I want you to know why. I want you to understand exactly why it is that we have to check this condition. So let's dive into an example right now so I can explain it to you. All right, so here's the example we're going to take a look at to help you understand the 10% condition. So let's say that we have a jar containing 20 marbles, 7 red, 13 blue. That's 35% that are red, 7 out of 20, and 65% that are blue, 13 out of 20. Now let's remove 5 marbles one at a time. That means we're going to take out a sample of 5 without replacement. That means we were withdrawing 25% of all marbles from the jar. 5 out of 20, 25%. Now, maybe we're going to ask a probability question. What is the probability that all 5 are red? All right, well, let's start with the first marble being red. Well, 7 out of 20 marbles are red, so 35% chance that first marble is red. Well, if we don't replace, that means the probability that the second one is red is going to be 6 out of 19. 6 marbles left in the jar that are red out of 19 total marbles. That's 0.316. So you see how the probability has definitely changed. Then for the third marble, we have 5 out of 18, 5 red out of 18 left. That drops down to 0.278 or 27.8%. That fourth marble, there's a 4 out of 17 chance of it being red. And that fifth and final marble has a 3 out of 16 chance of being red. So we see how the probability has changed quite a bit for getting a red marble. Well, because we're not replacing. Now that's going to give us a total end result of 0.00135 or about 0.135% chance that we're going to get all 5 red marbles. Now if we did replace every marble each time, well then the probability of getting a red marble would stay 7 out of 20 or 35% for the first, second, third, fourth, fifth draw, and that would give us a probability of 0.00525. So we see a very noticeable difference in our answers if we replace versus not replacing, and that matters. All right, but now let's up it up a little bit here. Let's say that we have a much bigger jar, this time containing 10,000 marbles. 3,500 are red, still 35%. 6,500 are blue, still 65%. And once again, let's take out 5 marbles. But now this time, we're only taking out 5 out of 10,000 marbles. That's only 0.05% of all the marbles in the jar, clearly under 10% of all the marbles. Now let's calculate the probability that all 5 marbles are red. Well, the first time we reach in, there's 3,500 red marbles out of 10,000, 35%. And if we don't replace that second marble being red, well, there's 3,499 marbles left that are red out of 9,999 marbles. Again, that probability is slightly, but just slightly lower than 35% at 0.3499. Then we got that third marble, very small change, but you see the idea. There's only 3,498 red marbles left out of 9,998 total marbles. And then we see for that fourth marble, another small change. And then for that fifth marble, another small change. And then that gives us a final answer of 0.00524. And again, that was sampling without replacement. Now, what about if we sample with replacement? Well, once again, that means it'd be 35% for the first, second, third, fourth, and fifth marble. That gives us 0.00525. Now, if we compare the two answers, the one that if we don't replace versus the one if we do replace, notice that the difference between those probabilities is, well, negligible. It's very, very minute. It's all the way to that fifth decimal place where we see a small change, but it might as well be the same. Now, if we bring in the example from earlier when we only had 20 marbles in the jar, we see a significant difference in the probability. So here's the deal. In that very bottom example where there was only 20 marbles and we took out 5, we were taking out more than 10% of the population. We were taking out 25% of the population. And we noticed that when we do that, we get a very different answer than if we sample with replacement. But in the middle example there, when we were looking at 10,000 marbles, and yes, we were taking 5 out, but it was such a small amount. It was only 0.05% of all the marbles in the jar. We noticed that we get an answer that is, again, very, very similar to what would happen if we replaced. So this is the idea. If you take out under 10% of the population, yes, there is a difference. Technically, you are violating independence and you have slightly different probabilities, but they're very slightly different, and it's to a point where it just doesn't matter, so we can assume independence. So again, we see that's 0.35, 0.3499, 0.3499, 0.3499. I mean, it's a very small difference. Whereas in the jar of 20 marbles, we had a noticeable difference in all of those probabilities. Now, the problem gets even less of an issue if we get an even bigger jar. Let's say one contains 10 million marbles, 35% red, 65% blue. Well, here, we could take out 5,000 marbles and we're still way under 10% of the population, so we could still assume independence. So you can see that the 10% condition really helps us in the situation when we sample without replacement. It really allows us to take out a sample without replacement and not have to worry about violating independence, even though we technically are. The difference if we did or didn't is very negligible as long as the sample size is under 10% of the population. That's exactly why we check it, and hopefully this example kind of showed that to you. Now, why is the 10% so important, and what are some situations when it's used? Now, we check the 10% condition when we're working with sampling distributions of sample proportions. We also do it when we're working with sampling distributions of sample means, and we use it in the binomial approximations for sampling without replacement. That's kind of the example we did in this video with the marbles. And we also need to check it when we're working with confidence intervals and significance tests, because the basis of a confidence interval and a significance test all hinges upon looking at many, many, many samples that you'd see in a sampling distribution. And, well, we need those samples to all be independent of each other. So you see that sampling is really, really an important part of statistics. Whether it's probability, sampling distributions, or hypothesis tests and confidence intervals, it's really important. But when we sample, we need to make sure our samples are independent of each other, and that gets violated if your sample is too big. It's too big of a proportion of that population. So that's when the 10% condition comes in and says you're totally fine to assume independence as long as your sample size is under 10% of the population.